Hello guys, I am Kalidas Tapadar. Welcome to Quality and Welding Metallurgy. Today we are discussing on slag-metal reaction. Slag-metal reaction, throughout the discussion, reference will be made to the both fluxes and slag. For clarity of description, the word flux will be the use for material which has not been melted in joining process, and slag will be used for the liquid phase formed during fusion and the solidified glassy product left in the joint area after joining. Flux made from mineral compounds, for example silicate, fluorspar, limestone or calcium carbonate are used to shielded arc welding process for atmospheric gases. The flux themselves may react to some extent with the molten weld metal. Slag metal reaction in welding process are difficult to analyze fundamentally due to the chemical complexity of metal phase and particularly the slag phase. Commercially, flux formulation are chemically complex due to the variety demands placed upon them during the joining of metal. Some of the metal may even conflict. For example, arc stability, weld metal toughness, bed shape and ease of solidified slag detachability from the joint must all be satisfied at once, at last to an acceptable degree. Reaction between slag and metal during welding can transfer elements from the slag to metal or vice versa. The discussion of slag-metal interaction involved reaction of following type: manganese oxide per ferro is equal to percentage of manganese ferro plus ferro oxide, silicon oxide ferro is equal to percentage of silicon ferro to ferro oxide, like this. The discussion of slag metal interaction involved reaction of the following types. Slag metal reaction: if reaction of the type outlined are conducted at the suitable elevated temperature to provide enough energy to reaction to proceed rapidly and long enough time for the reaction to finish completely, the reaction reach its final equilibrium state. This is often the case during the steel making operation, from which most of our knowledge of pyrometallurgy comes. What is pyrometallurgy? Definition of pyrometallurgy: the branch of the science and technology concerned with the use of the high temperature to extract and purify metal. That's all. In welding operation, temperature can be very high, but duration is very short, in the order of second or even fraction of second. And increases in temperature will normally make a reaction process more quickly. A short time likely to reduce the extent of the approach towards equilibrium. Thus, welding process have two prime conditions which conflict, one increasing the reaction rate and other effectively reducing it. Therefore, the considered two aspects of slag-metal reaction, the equilibrium condition for the given reaction, which represent the maximum achievable extent of the reaction, and the kinetic of the physical situation, which will be determine how close equilibrium a given reaction condition is like to get. As we will see, mass transfer processes are critical in moving reaction product to any way from reaction site, and thus have a crucial role to play in the achievement of equilibrium condition. The equilibrium condition can be assessed as calculating an effective equilibrium temperature for a variety of alloying element and associated slag component in weld. Thus, an average re-effective temperature is an appropriate assessment. Acknowledgement that may alter for the some reaction in differing welding circumstance. If the calculation is done for several alloying elements individually, it is often seen the wide range of equilibrium temperature occur for the different reaction in the same weld deposit. Slag-metal reaction, since the calculated equilibrium temperature for individual reaction differ, equilibrium was not achieved for all, if any, of reaction. Look at another way. If each possible reaction was assessed at a fixed temperature corresponding to that of the slag-metal interface, say 1800 degrees centigrade, and equilibrium concentration for all of the alloying element in the metal could be found if all necessary thermodynamic data were available. In our deposited weld metal, we would then find that the actual composition varied from the equilibrium projection, that the reaction could be incomplete in most cases, like did not reach equilibrium. For example, if equilibrium level of manganese in steel weld, manganese steel weld is calculated to be 1.5 and the weld content 0.3. The reaction can be crudely described as 20% completed. All of this suggests that there is interference of varying magnitude with the sum or all the kinetic process which control mass transfer away from the slag-metal interface into the bulk slag and metal phase. Slag-metal reaction in electroslag process are fundamentally controlled by two factors. One of the first, the thermodynamic driving force defined by the net force energy favoring the reaction and chemical activity of the reactive phase, reacting phase, sorry. This determines state of equilibrium achieved at the slag-metal reaction, the active area of discussion on gas-metal reaction. The second one, the rate of adjustment gases. The rate of gases transport in the slag and metal phase, which determine the degree to which the bulk metal and slag composition approach the interface composition. The following discussion will look first at the situation where reactive compound in the slag element into the metal phase, like slag to metal transfer. This can occur deliberately, for example, in SAW, submerged arc welding procedure, where manganese and silicon in the weld metal are provided largely from the flux. The section will assess the situation where the reactive compound in the slag phase remove alloying elements from the metal phase, transforming them as compound into the slag phase, like metal to slag transfer. This can cause alloy loss and force the need for compensatory action, which ensure that chromium lost by slag oxidation is replaced. Slag metal transfer, where the thermodynamic driving force is high, transfer is controlled by diffusion of reaction through a boundary layer in the slag phase. The reaction rate is so high that a complete exchange takes place between the reaction phase, resulting the 100% weight concentration of reaction product at the interface. Three subdivisions exist based on the physical nature of the reaction product. First one, liquid. The boundary layer is thin but about 1 to 10 micrometer thick, and reaction go to the complete. Rich equilibrium in most cases. Example are the reaction between ferro and slag containing oxide or halides of nickel. Gases. The evaluation of gaseous reaction product at the slag metal interface increase the effective boundary layer thickness about 100 micrometer and interface with diffusion of reacting phases to the slag metal interface. The reaction rate is therefore slowed down, and true equilibrium is not achieved in the time available for welding process. Examples are the reaction between ferro and slag containing nickel chloride to form ferrochloride, or between aluminum and slag containing copper chloride, which form aluminum chloride. Ferrochloride boil at less than 700 degrees centigrade, 1290 degrees Fahrenheit, while aluminum chloride boiled at less than 200 degrees centigrade, like 390 Fahrenheit. Third one, solid. In its case, in this case, the effective area available for the slag metal reaction is reduced by the formation of solid phase at the interface. The reaction can forced only at the gaps where that solid phase is temporarily absent or lifted by slag motion. An example of this reaction between aluminum and slag containing copper oxide. Aluminum oxide melt at 2045 degrees centigrade, 3710 degree Fahrenheit, while aluminum melt at 660 degrees centigrade and 1110 degree Fahrenheit. When there is a very limited thermodynamic driving, that overall reaction rate is controlled by the ability of steering force in the liquid metal to remove reaction product from the slag metal interface and mix them into the bulk metal. The equilibrium state at the interface is characterized by concentration of reaction product of a few % of or less compared to the virtual 100% weight achieved where a high driving force exists. The concentration gradient from the interface into the metal is therefore much reduced, as the resulting rate of mass transfer via diffusion away from the interface into the bulk metal, where steering force distribute to the reaction product throughout the molten metal. The mass transfer rate drop as the bulk concentration approach the interface concentration, because the concentration gradient is continuously decreased. True equilibrium is therefore not achieved. Example for the reaction between ferro and the oxide of silicon, manganese and phosphorus, where the reaction products are liquid and no kinetic barrier exists. Liquid and no kinetic barrier exists. Deoxidation in the ferro can increase the effective rate of mass transfer by increasing the rate of removal of a reaction product from the interface, thus increasing the rate of the increasing of the other part like removal oxide from the breakdown of an oxide such as manganese oxide, increasing the rate of manganese transfer. Metal to slag transfer. Transfer of alloying element out of metal phase by reaction with a slag is ultimately limited by the rate of supply of the element in question to slag metal interface by the steering force in the metal and diffusion through the static boundary layer next to the slag metal interface. As the bulk concentration in the metal drop, the concentration gradient is lowered and the process of the mass transfer becomes very slow. Equilibrium is not achieved but is closely approached if the thermodynamic driving force is high. Subdivisions are based on physical nature of the reaction product, like liquid. Liquid transfer is rapid at first but slow down as bulk concentration in the liquid is reduced. An example, the reaction between ferrosilicon alloy slag containing ferro-oxide. Silicon is lost the slag as silicon oxide too. Gases. Gases form in the reaction between the alloy metal and reacting slag occur initially at the slag-metal transfer interface and then slag-metal interface and then within the bulk metal as well when the steering force distribute the reaction product like alloy elements and associated atom from compound in the slag. Metal to slag transfer, this gas ebullition causes fragmentation of the molten metal which in turn increase the reaction rate by exposing more metal surface to the slag. The resulting variation in localized reaction rate causes a large scatter in final metal composition. The scatter is function of the large variation in surface area, volume, ratio caused during fragmentation. An example is the reaction between ferrocarbon alloy and ferro-oxide in the slag. Oxide is dissolving in the ferrocarbon alloy at the slag-metal interface during the thermodynamic breakdown of ferro-oxide in the slag and swept into the ferrocarbon alloy by steering force. Carbon is then lost from the metal as carbon oxide gas when the dissolved oxide reacts with the dissolved carbon within the ferrocarbon alloy. Therefore, true equilibrium exists at the slag-metal transfer interface, exists at the gas-metal interface for the general cases, and is achieved in the bulk metal only when the thermodynamic driving force is high and the physical nature of the reaction product is suitable liquid. In general, kinetic barrier prevent true bulk equilibrium. Metal to slag transfer, there are reactions take place primarily at the electrode tip. Since surface area to volume ratio is very high and steering force are strong due to sudden change in current density, the extent to which equilibrium is achieved dictates the amount of alloying element gained or lost and simultaneously absorption of oxygen or other tramp element can strongly affect toughness and other mechanical properties. Thank you.